All right, let's get started with our first chapter. Now, this first chapter is not anything too crazy. We're just going to kind of look at a little bit of an overview, an introduction to understanding what it is we're going to be looking at in chemistry. Okay, so when you think chemistry, everybody starts thinking, oh, chemicals. So what are chemicals? Here we have a picture that has got a picture of a kitchen and a bunch of things that you find in a kitchen. Okay, so we've got your refrigerator, which is a metal alloy. If you have a gas burning stove, you'll have some natural gas there. Usually it's the same gas that we use in our Bunsen burners in lab. A lot of fruits, they're grown with pesticides, fertilizers. I don't know if you've ever, when you buy a piece of fruit, hopefully you wash them, but a lot of times there might be some sort of residue on them, okay? There's polymers everywhere. If you have glass in your kitchen, usually that's silicon dioxide. Our water, it's treated with lots of different chemicals. So for a long time, we've had fluoride added to our water, and there's a lot of other dissolved stuff in our water. What dissolved stuff and how much dissolved stuff usually varies from region to region. In San Diego, we have a whole bunch of different areas of town where we get water sources from. And so if you test water at my house versus testing water downtown at school, they might be a little bit different with their dissolved stuff. But the main point is that there's nothing that we touch or hold that is not made of chemicals. So they are all around us. And so hopefully this semester, you'll gain a better understanding of some of these various different chemicals that we have around us. So what is chemistry? So here's a textbook definition for you. Chemistry is the science of the properties, composition, and behavior of materials. What we like to do in chemistry is we like to describe and explain these different forms of matter and the reactions that we have. So in this picture right here, you can see that there is an ocean and a beach and a whole bunch of buildings, so probably some sort of city here on the West Coast. But it's all kind of gross looking. The air doesn't look real great. Well, one of the things as an environmental chemist might try to understand, well, what's in that air? In air that's gross like this, we have some NO2, okay? NO2 is known as nitrogen dioxide, and it's part of a class of chemicals that we put as NOx, where that X can represent any number of oxygens. There's a lot of different nitrogen, oxygen compounds out there that have various different numbers of oxygens that are involved as pollutants in the air, okay? And so again, we like to describe, explain different forms of matter and our chemical reactions. And this semester, we are going to learn why did that NO2 get named nitrogen dioxide. We'll learn about looking here, why that kind of has a little bit of an angled shape to it. We'll learn how everything bonds together. We'll learn about some reactions that occur and maybe understand a little bit more of what's going on behind that nitrogen dioxide and what it does in our atmosphere and all sorts of other types of reactions. Now, when we talk about chemistry, we can subclassify it. Okay, we have applied chemistry. So applied chemistry is a lot of what you're going to see in industry, where we're looking for something that's useful. Maybe in pharmaceuticals, our search there is we're trying to find some sort of drug that works really well to treat a disease or to battle cancer or to have better pain relief. Okay. Then we have our theoretical chemistry. A lot of what happens at a university campus ends up being theoretical chemistry. And so what we're trying to do in theoretical chemistry is we're trying to explain nature. We're trying to explain these natural processes. Within theoretical chemistry, we have a few other branches. There's organic chemistry, there's inorganic chemistry, biochemistry, physical chemistry, okay? And so we have sub-classifications there. And then we can even classify further than that, okay? So we can take chemistry and our inorganic chemistry. We're looking at elements, properties, preparation, applications of compounds. Inorganic chemistry usually is a lot of it's really colorful, especially work that's done with transition metals. We can get some really cool colored stuff. Organic chemistry, that's looking at carbon and its compounds. If you're taking this class because you are hoping to go into nursing someday, you should end up having to take Chem 130 after Chem 100, and that is going to be an organic chemistry course. Physical chemistry, it crosses over a lot with physics, and there's a lot of theoretical and mechanical things. We'll talk a little bit about physical chemistry this semester. We don't do a whole lot with it. Personally, a little bit of my background, I am not a physical chemist. Physical chemistry was probably the most difficult of my chemistry courses for me when I was in school. Biochem, we're looking at reactions within living systems, and then there's my branch, analytical chemistry. So the textbook definition here says study of constituents and identification in chemical substances, but there's a lot of things that we can do with analytical chemistry. So I happen to work all on organic molecules. I did something called redox-dependent hydrogen bonding. That may sound like complete gibberish to you now. By the end of the semester, you will understand what redox means, and you will understand what hydrogen bonding means. What was interesting about what I did is we were looking at very basic, very tiny molecular recognition systems, host-guest systems, trying to figure out whether or not we could make sensor technology better, make things better on an on-off switch at that molecular level. Electrochemical sensors are used in a lot of different places. If you know anybody that is diabetic that has to test their blood sugar, okay, those meters are a type of electrochemical sensor. Now, most people, when they specialize in something, they get kind of full of themselves and they get very into, well, this is my thing and it is more important than everything else. And so chemists like to say that chemistry is the central science and that all other sciences tie into us. And some of them are super obvious, like medicine ties into chemistry in a lot of ways. Pharmaceuticals, that's all chemistry there. Trying to understand reactions that happen in the body, nutrition, very, very based on chemistry. Biology, okay, same thing. We start to get, all those reactions in biochemistry with living systems. So then we branch into biochemistry itself, where you get even more into the chemistry angle and less into the biology angle. Physics ties into chemistry when we look at the structure of an atom and what happens within an atom. When we look at spectroscopy, when we talk about material science. Environmental science, we had a little bit of an example there a couple slides ago when we looked at that gross smoggy sky, and now we have to start to understand, well, what's making it all smoggy, what molecules are in the air, how did they get there, what are they doing once they are in the air. Plant science, okay, there's some really interesting stuff when it comes to plants. There's a flower that the color of the flower is different depending on the pH, so how acidic or how basic the soil is. So if the soil is more acidic, it's one color. If the soil is more basic, it's another color. Okay, there's astronomy. What's really cool is we can, using spectroscopic techniques, figure out what elements are in distant stars and or around distant planets. Okay, and then geology, all of our rocks and minerals, those are all composed of chemicals. One of the things that hopefully you'll get out of the semester is thinking like a chemist. So when we look at an image like this, okay, I'm a chemist. My parents are not chemists. My husband is not a chemist. Okay, they all might think of things a little bit different. My mom or my husband, they might look at this and go, oh, we see, a nice lake or beach. There's some sand there. My 3-year-old would immediately look at this and get very excited because the adult and the child are both wearing pink and sitting on a pink blanket. All right. So that's how a lot of other people think. But as a chemist, I look at this a little different. Okay. First thing that comes to my mind is, well, is this a freshwater lake or is this a body of water like at the ocean? What's in there? Are there salts? Are there minerals? What sorts of things are floating around in there? And so I start to picture in my head what might be in that lake. Like this right here, that's a water molecule. Water, if you don't already know, is H2O. Okay, when we have symbols, when we have drawings like this, oxygen is very frequently, almost always represented by a red dot. Water has one oxygen in it, so we've got that red dot there. Hydrogen is represented by white or grayish dots. There's 2 hydrogens, so we've got the 2 white dots there. So this would be O2. That would be an oxygen molecule, okay? And then there's other stuff floating around in there. And so as a chemist, I start to think like that. The sand, what's the sand composed of? Okay, so that's how we want to start thinking, is looking at things on more than just a surface level and starting to probe within them to understand what they're composed of. Okay, when we study chemistry, there are some things to keep in mind. Be curious. This is science. We ask a lot of questions, like with that think like a chemist. Okay, ask those questions. Be curious. Probe deeper. Okay. In fact, I even put on the slide, ask questions. Ask yourself questions. What is interesting about something? And try to delve deeper than that. If you don't understand something, ask me, okay? I have office hours, I have email, we have Canvas, lots of ways to get a hold of me. Learn your vocabulary and nomenclature when we get to it. So you gotta understand the language behind chemistry. Just because we run the class in English doesn't mean there's not a lot of terminology to learn. Keep current with the class. Don't wait for tests. This is why I have you turn your notes in, especially with an online class. This is so important to keep current. It's so easy in an online class. Just be like, yeah, whatever. I'm not going to worry about the lectures. And then you get to getting ready for a test and you go, oh, I have 4 weeks of material I have barely looked at. Okay, so I do have you turn your notes in to make sure that you are actually keeping up with and pacing yourself properly in the course. Study groups are great. I had lots of study groups in college. My favorite one, we had a group of us that were taking calculus and physics together, and we used to meet at a Denny's near San Diego State University, and we would study there till like 2 o'clock in the morning. And it wasn't just great for making sure we understood the material, but it was great to have a group that was going through the same classes together, so we could all kind of commiserate with each other, and when things got really frustrating, we could help bolster each other up and then delve into our course material and work problems. Don't just copy down what I do in slides. Okay, after you've finished a lecture, maybe pull the blank slides and try the example problem again and see if you can do what I did on your own before going back to your notes. Okay, so working the same problem over and over again to make sure that you understand how that problem is done is really crucial. Okay, now, when we go through science, we also need to understand the scientific method. All right, so we have some sort of an observation. This observation will describe something that we see, that we hear, that we taste, that we feel, that we smell. Okay, now what I can do is, let's say it is the first week of classes and I walk into my office and I comment to one of my colleagues, oh my goodness, the parking lot is really crowded today. There is my observation, okay? I can see that the parking lot is crowded. Now, I can come up with some sort of conclusion to myself. Okay, I can make some sort of hypothesis. I can make an educated guess based upon this observation. Oh, well, there's a lot of people in the parking lot today. Oh, I think there's something going on campus. Well, maybe I need more than one observation. Okay, because notice here I have a series of observations. Maybe I take, a few things in consideration, like one, lots of people, lots of cars. Okay, maybe number 2 is lots of people on campus. And maybe number 3 is I see large crowds outside classrooms. Okay, so then maybe my hypothesis here is that classes started. All of a sudden, there's tons of people parking, there's tons of people on campus, and there's lots of students waiting outside classrooms. So my hypothesis is that classes have started. So then I can turn to the scientific method. Okay, so there's my observations, my empirical facts. Okay, now sometimes we have scientific laws, so we have some things that we've tested already based on consistent observations. I can put things together in a hypothesis, and then I can test that explanation. I can test my observations and make sure that I come up with something cohesive. Okay, so I can expand my scientific method into this right here. So my observations, I made 3 observations. Okay, I did that part. Hypothesis, I did my hypothesis. Now, my prediction. Okay, I predict that if I go and query people that are standing outside classrooms, they will tell me that they are there because classes have started. Okay, so I have predicted what's going to happen. Now I can go run my test. Okay, now I can actually go talk to all of these students and say, hey, why are you here? And they might say, I'm here because classes started today and I'm waiting for my class to start. Okay, if that works, woohoo, my hypothesis is tested. I can make my theory. I can do some more tests. Maybe I travel to a different classroom and I ask those students. They corroborate what the previous one said. Bada bing, done. Okay, it worked out well. Now what happens though if I strike out here? What happens if I go ask this crowd outside the classroom and they tell me that they are there for a special event, not for classes? Okay, well then I have to reject my hypothesis. Now I have to come up here and go and make a new hypothesis. Okay, maybe all these increased people are on campus because we are hosting a conference. Not classes was started, but San Diego City College is hosting some sort of conference. Okay, make my new prediction. I go ask people and they start telling me, yeah, I'm here for this special event. Yeah, we're having, a conference for high school students that want to major in STEM subjects, and now we're all here for this. Or maybe we're hosting a conference for fellow educators and we've all traveled to San Diego and now we're waiting for our different sessions. And so it's an iterative process. We don't always get it right the first time, okay? We use what we have to make the best prediction possible, but we don't always get it right. So I want you to ask yourself, where do we learn more? Okay, do we learn more if we've supported our hypothesis right away? Or do we learn more if we reject our hypothesis and we have to go back up here and rethink it? So think about that to yourself. Where do you think we might learn more? Okay. Now, before we finish off this chapter, just so we start getting some of that terminology down, we're just going to briefly go over a couple more things. Okay, one thing to understand is that scientific discoveries, you don't have to memorize any of this. I just think this is really interesting. If we look at this, the law of gravity was back in 1687. We figured out oxygen in 1774. We figured out an electric battery in 1800. And then in the 1800s, you can see there are a whole bunch of discoveries. But then when we get to the 1900s, we get even more discoveries. So it's really cool about science is like it took a long time to start to discover things, but then as we started being able to do more and we started developing better technologies and better tests and things, we were able to start really exponentially ramping up all of our discoveries. Okay, and then now in the 2000s, what else are we going to discover? Okay, just a few more here. Just understand some of our terminology when we relate to matter. So what is matter? Okay, anything that occupies space and has mass. What is mass? We want to think of mass, okay, it's the amount of matter that an object contains. So when we mass something, we usually use grams or kilograms. Okay, so that's a little different than weight. Mass is related to inertia. So a tendency of a body at rest to be at rest. So mass, again, is just the amount of matter that an object contains. My mass on planet Earth is going to be exactly the same as my mass on the moon. My weight, however, changes between Earth and the moon. Because what is different about Earth and the moon? Gravity. Weight is simply the effect of gravity on matter. So the amount of mass you contain does not change from one place to another, but your weight might change based upon gravity. We have 3 different states of matter. We have gas, we have liquid, and we have solids. Gases we will go over in more detail toward the end of the semester. I have us slated to start talking about gases in week 13. So we'll learn more about gases then, but one thing about gases, they expand, okay? So they have no definite shape, no definite volume. They fill their container, they bounce around randomly. Liquids, constant volume, they take the shape of the container, well, the shape of the container bottom because they rest at the bottom. There is random particle motion, but it is a fixed volume. And our solid, constant volume, constant shape. What's interesting is the particles still vibrate in place, which I will try to show you an example of that later. Okay, and so here is kind of a fuzzy image, but you can see our gas expands to fill the container, the liquid has a definite volume there, and then the solid, definite volume, definite shape. We can go between states of matter by cooling or heating. When we talk about solids, there's a couple different types. There's crystalline and amorphous solids. So this is the most common is crystalline, so salt, quartz, etc. We'll look more at this later this semester. Crystalline solids, they're crystalline because they exist in regular repeating 3-dimensional patterns. Amorphous, things like plastics, glass, gels, okay, they do not have a regular pattern. And so here is a picture. So silicon dioxide, we can get 2 different forms of it, quartz or glass. Okay, and so our quartz is crystalline, we've got that regular pattern. Our glass is amorphous, we get a non-regular pattern. That's why if you drop a piece of glass, it shatters into very random pieces. It's because it's amorphous. Okay, and then we can go between our states of matter. All right, we can take a solid and heat it up and get a liquid, and we can take that liquid and heat it up further and get a gas. We can take gas and we can condense it, cool it down, and get a liquid again. We can take that liquid and freeze it and end up getting a solid. Some substances will allow us to go directly between solid and gas and solid. If you've ever dealt with dry ice does this. We go directly from the solid to the gas, and then if we were able to trap that gas and cool it back down again, we would go directly from the gas to the solid. In your labs this semester, you will get to see a demo of something undergoing sublimation. Iodine mostly sublimes. There's a little bit of liquid, but you don't really see it, so it appears as though it's sublimed. So when you watch it, it'll go directly from the solid to the gas, and then directly from the gas back to the solid. So it's a really cool demo that you'll get to see. When we do this further classification of matter, we can get a pure substance. So one substance only, it's got a definite composition, definite properties. Or we get a mixture where we have 2 or more substances. And so the properties are going to depend on the composition there. And what's interesting about mixtures is when we talk about liquids and solutions later this semester, we'll talk about something called colligative properties. And when I make a mixture, like let's say I dissolve something in water, well, it changes those properties. So water would be a pure substance, and then whatever solution I make would be a mixture. And so we can exploit these properties too. If you've ever lived somewhere where it gets super cold, you might have had to put antifreeze in your car's radiator. Well, antifreeze is a mixture of water and ethylene glycol. And what happens in that mixture is the presence of the ethylene glycol lowers the freezing point of the water. So instead of freezing at 0 degrees Celsius, it freezes at a lower temperature, thus hopefully preventing the water in the radiator from freezing and then cracking the radiator block. With pure substances, we can get an element, so we cannot separate those chemically into simpler substances, or we can get a compound like water, which we can separate into simpler substances. So water would be a compound, H2O, because we have more than one element there. And then there are chemical methods to separate that into oxygen gas and hydrogen gas. Okay, Mixture, we get a homogeneous mixture or a heterogeneous mixture. So homogeneous, uniform appearance, we can't tell one particle apart from the other. Like if you make coffee in the morning and you put sugar in your coffee, you can't tell the difference between the coffee, the caffeine, and the sugar. It all looks like one uniform thing. Heterogeneous, we can see the different parts in there. So like, let's say you make hot chocolate and you put marshmallows in your hot chocolate. That would be a heterogeneous mixture because you can absolutely, with your naked eye, visibly see the difference between the hot chocolate and the marshmallows floating there. Okay. So when we start to do this, we like to, classify things. So like aluminum. All right, based on what we had here, aluminum is going to be an element. We cannot separate it chemically into simpler substances. Okay, so it's going to be matter, it's going to be pure, and then it'll be an element. All right, so we can't decompose it into simpler substances by chemical reactions, so therefore it is an element. Okay, now aluminum can make compounds, so oxides of aluminum occur naturally. Rubies and sapphires are oxides of aluminum. Oxide means it has oxygen with it. We can also alloy, okay, into mixtures. So an alloy, you take one metal, you take another metal, you melt them down, you mix them together, and usually then they re-solidify. Okay, so these would be compounds here. This is an element. Okay, and then our different alloys would be mixtures. So we can do a lot with our different elements. We can do a lot of different things with mixtures and a lot of different things with compounds. Now, as we start going through the semester, okay, you will get familiar with a lot of the periodic table, but the elements I have highlighted here in yellow, these are elements that we will start working with a lot more, that you will see more frequently than some of the other ones. So these are ones to start getting familiar with. Now, if you've never used the periodic table before, you are not going to be very familiar with what the symbols and the names are. Let's see here. Your textbook does have a copy of the periodic table that does have the symbols with their names. So you can start to learn that something like H, this is hydrogen, okay? Or B, this is boron, okay? Or maybe this Hg, this is a weird one. Hg, the symbol for this element comes from the Latin name, okay? Hg is mercury, okay? And so now versus later is a good time to start getting familiar with these. Don't wait until we get to chapter 6 in week 5 when we do our nomenclature to start learning all of these. Start learning to pair the elements and the symbols now. That way you get familiar with them, and as we start going through everything, you will be able to speak that language of chemistry sooner rather than later. All right, so this was our first chapter. Our subsequent chapters will be broken into some smaller videos. I'm not going to make you sit through an hour and a half long video for a longer chapter. I will break the videos into smaller pieces so that way you can focus on specific topics. This first chapter, though, is just kind of an overview of things, so I just use it all lumped together in one lecture. So make sure that you have your notes ready to go. I don't mind if your notes are handwritten and then you scan them or take pictures of them. I don't mind if you have done your notes on an iPad like I'm using here to do these lectures. Just as long as you have taken notes, you will make some sort of image of your notes, and then you will upload your notes to Canvas to receive credit for having basically attended class. Watching the lecture videos and taking notes on them, that is your course attendance for an online class. So make sure you do get those notes uploaded. Make sure that when you upload things, they are in the correct orientation. If you have written it in a vertical form and then it shows up horizontal, I get a horizontal image and I can't really do a whole lot with that because the Canvas app does not allow me to rotate images within the app for grading purposes. So make sure that your files are oriented correctly. I do have unlimited submissions enabled. That way you are able to fix something once you have reviewed it. It is your responsibility to make sure that your submission is done correctly. All right. So once you have done that, you can go ahead and pop into chapter 2 and start taking notes on that. Or you can get into Wiley Plus and look at the homework set for chapter 1 and start working on that. Up to you how you want to do that, but take a look at that schedule, look at when things are due to kind of help pace yourself throughout this semester.